talk. So this talk is based on a line of recent work over the past 2 years or so. And these are all the co-authors that have worked on the line of work, and quite a number of them are in the audience today. So let's begin with the basic definitions. I know everyone here is an expert already, but just to start us off with, we'll define the min cost flow problem. So for this problem, as input, we're given a graph G with n vertices and m directed edges. We have vertex demands, and these demands add up to 0. So positive demand means you want flow coming in, and negative demand means you want to send flow out. And we also have edge capacities, non-negative edge capacities, and also costs for every edge. And the output for the algorithm should be a flow minimizing the total cost and satisfying the constraints and routing the demand. Okay, so we're also going to talk about general linear program solvers. So this is a general linear program written in standard form. And just to remark, so here we're using the constraint matrix A, and A is going to be n by m. So m is the number of variables, which might get a little bit confusing, but the reason we choose to do it this way is because for flow problems, m is the number of edges. So we want that to be representing our number of variables. So for general linear programs, they don't necessarily correspond to any graphs, but we still want to be able to associate a graph with these linear programs. So what we do is we look at the constraint matrix. So we look at the matrix A, which has n rows, and we assign one vertex to each row. And for the m columns of A, we basically treat each column as a hyperedge, or equivalently, you can think of it as a clique. So in a column, you have a certain number of non-zero entries, and the hyperedge will contain all the vertices for which the row is non-zero at that column. Okay, so I hope that's clear. And the reason we define this dual graph this way is because in the case of the min cost flow problem, if we look at this constraint matrix B transpose, we treat that as A in the original general linear program formulation. Then B transpose here is the adjacency matrix of the input graph G. And the way we've defined the dual graph means that the dual graph of this linear program formulation is exactly the adjacency matrix of the input graph G. Okay, so stepping back a little bit, we also want to define the tree width of a linear program. So again, general linear programs do not necessarily correspond to any graphs, but because we've defined this dual graph, we can talk about the tree width of the dual graph as a graph. So we say the tree width of the linear program is the tree width of the dual graph. And similarly, we'll want to talk about separable linear programs. And here we say a linear program is separable if the dual graph is separable. And we'll get into like separability definitions a little bit later. Okay, so we talked about min cost flow linear programs. So these are some of the current state-of-the-art results for research in this direction. And in my talk, I'll be focusing on these 5 that I've highlighted. And basically, they're all on graphs or general linear programs that exhibit like specific structural properties. So we have planar graphs, we have tree width T graphs, and then we have alpha separable linear programs corresponding to alpha separable graphs. And yeah, so all 3 are, they admit very nice balance separators that will really make use of in our algorithms. And for these classes of problems, we have the state-of-the-art result. So we have nearly linear time algorithm for min cost flow on planar graphs. And that was an improvement from m to the 1.5, or also n to the 1.5, because m equals m and n are on the same order. The n to the 1.5 result is the Spielmann-Tang result. I think that's about, I wanted to say about the results we get in our algorithm. Okay. So let's jump into what happens in these algorithms. So we'll be using interior point method as is common in this line of work. And just as a very general brief overview, in the interior point method, usually, so here we have the polytope. So here I'm only talking about the primal solution, but we're doing primal dual interior point method. So here's the feasible set. So this is polytope, and this is the optimal solution we're going towards. And the red line here is the central path. So the idea of the interior point method is that you start off with some point on the central path that you're trying to. So first you need to find a feasible point inside the interior point, inside the polytope, and then you try to move towards some point on the central path by taking a Newton step. And then you basically move along the central path to a different point, and you move your solution to try to follow that point. And then you, on the central path, you take you move along the central path again from the second point to the third point, and you want to move your solution closer to the third point on the central path. And by doing this, you just kind of follow this central path towards the optimal solution. Okay, and in robust interior point methods, what we do is a little bit different. So we have our initial point, initial feasible point in the polytope. And what we do is we also keep an approximation of the solution. So x1 is our current solution, and then x bar 1 is the approximation to the current solution. And this is going to be a coordinate-wise approximation. And now we want to move. So basically, x1 is kind of corresponding to this point p star 1 on the central path. And now we kind of want to move closer to p star 2. So in regular interior point method, we would use x1 to calculate the direction to go in order to get closer to p star 2. But with robust interior point method, we use x bar to calculate the direction we want to move in. So what happens is that because we're using the information at x bar instead of at x, we could take bigger steps that bring us further away from the central path. Okay, and then we get to our second point, x2, and we also maintain an approximation x bar that is coordinate-wise close to x2. And we use x bar again to find the step we want to take to get closer to p star 3. And then we find the approximation to x3. Okay, so the guarantees here are that it still converges in the square root m times log 1 over epsilon iterations. And also, we know that the steps have bounded to norm. And these will be really important for our data structures. Okay, so now that we have talked about how robust interior point method works, we can basically say we want to apply robust interior point methods to our linear programs. And this reduces to two data structure problems. So first is we have a current solution x for this robust interior point method. It's iterating, it's updating at every step by some delta x. So that's the step we're taking to move closer to the next point on the central path. And we know that the step that we're taking is going to be of the form p sub w v, where v and w are functions of x bar. So basically, we're using x bar to compute the direction that we're taking, and also we're weighting it so that we stay within the feasible set. Okay, so in regular interior point method, v and w would be functions of x instead of x bar. So that's the difference. And here, this p sub w is an approximate L2 projection onto the feasible subspace. So for some of our papers, we use the exact L2 projection, and for the case of flow problems, we can have a approximate projection, which allows us to have even faster running times. And the techniques that we'll use in order to accomplish this dynamic algorithm is to, for part one, do matrix and inverse matrix maintenance in order to maintain this P sub W. So at every iteration, because W is changing, this matrix is changing, and we need to be able to always use the latest matrix. And then the second technique is that at every step, we update X by a step, but we don't want to explicitly compute every coordinate of this update. So we'll have an implicit representation of X. And this also means that at every step, it's not very easy to just get all the information you want out of the current solution X. So we have to be clever about what information we actually need from X and when we want to be able to access everything. Okay, so part one was to maintain the current solution X, and part two is we need to maintain the approximation X bar. And here we can actually reduce this problem to finding heavy hitters in X. So basically finding large coordinates in X. And the difficulty here is that because X is not represented explicitly, we can't just look through the vector. That would cost order of n time. So we want to be able to find heavy hitters quickly, and we give a probabilistic algorithm for this part. Okay, so those are the problems that we're going to be solving again.
Yeah, can I just ask quick, what's the intuition for what's the difference between X and X bar again? Like, you could compute X, but why are you using X bar instead?
Oh, okay, so X is the exact solution of our current IPM iteration. And the idea is that computing X is going to be expensive. So
Okay.
typically it will take order of m times. M is the length of the vector. And because X bar is only an approximation to X, you can imagine if when we take a step, we don't have to update every coordinate of X bar. So now we have guarantees on how many coordinates of X bar we actually want to update. Okay,
so we have this like implicit representation of X, but we don't actually use it when we're making the next step. We use X bar instead.
So we don't use it to calculate where we calculate the step, but we need to make that step from the current X.
Okay, I got it. Thanks.
Yeah, okay, so these are the problems that we're trying to solve, and this implicit representation of X is what we called the multi-scale representation in this paper that was about linear programs for low treewidth matrices. And this is really long, and Guanghao worked really hard on it, but now it's all been simplified, so you don't need to read that paper anymore. And we actually, in our latest paper, simplified all the data structures, so now we have something a lot more modular, and the theorem basically says if the update to X is of the form this thing, then we have efficient data structures for everything. Right, so the update is P sub W V, and we want to be able to write this expression as this delta nabla, and I'll explain what that is. So this delta is going to be what we call a tree operator, and the nabla is an inverse tree operator, so one is triangle and one is upside down. And both of them are functions of the weights W from the IPM, because of course, this is a factorization of the matrix P sub W. And now when we say efficient data structures, we're going to mean like how fast we can do all the updates will depend on how fast we can work with these two matrices. Okay, so let's talk about how to actually get these tree operators and inverse tree operators. So now let's talk about balanced separators in that direction. So given a graph G and a constant B, and here we also say we're going to assign some weights to the vertices. We say a vertex set is a B-balanced vertex separator, B-balanced vertex separator, if when you remove the set from G, you get two disconnected components, A and B, and both of them contain at most small b fraction of the total weight. And of course, there's the famous theorem by Lipton and Tarjan saying that planar graphs have square root n size separators. The second one is not really a theorem. It's more like just the property of separable graphs that n to the alpha separable graphs have size n to the alpha separators. And finally, treewidth T graphs have size T separators. And really, this is the key property that we'll use. And these are, what differentiates the different cases that we have in our results. And then the framework we have applies to all three cases. So yeah, let's now talk about how to use a balanced separator to decompose a graph. And we'll use this planar graph, the grid graph on n vertices as an example. So what we'll do is we'll recursively use a balanced separator to decompose the graph until every piece is very small. So in this case, we want there to be no more non-trivial balanced separator. Okay, so for example, one balanced separator could be the third column in the middle, because when you remove these vertices, you get two halves. That are balanced. Okay, so by applying this separation recursively, we can get what we call a separator tree. And how this works is we start off at the root with the original graph, and here we say this is at level 0, and it's the 0th node at that level. We find a balanced separator, and then we split up the two sides. And for the edges within the balanced separator, we can just partition them arbitrarily to the two sides. Okay, so then we have two nodes at level 1. And again, we will find a balanced separator in this node, which we'll take to be this part in the middle. And that separates it into two smaller pieces. And we do the same thing on the other side. So edges in the middle get partitioned arbitrarily. And we can see that the height of this tree is going to be log of n. It has constant degree. Each node represents a subgraph of the original graph. And we get down to constant size leaf nodes. Some other interesting properties. So the union of nodes at a level is going to be the original graph. And also the edges altogether, the nodes partition the entire edge set. And another thing is that if you look at two sibling nodes, so these two, the intersection of their vertex sets is the separator at the parent level. Okay, and some other notation that are pretty important for us. So the boundary of one of these pieces is going to be basically the nodes where this piece is attached to the rest of the graph on. So the boundary for this bottom piece would be these vertices and then those vertices. And yeah, so the separator tree actually gives us a very natural partition of the vertices and edges in the original graph, and they'll be necessary for defining the tree operators. Okay, so we have this very interesting separator tree with a lot of structure, and now we want to say, okay, we use the separator tree to recursively factor the symmetric matrix, which shows up in this projection matrix P sub W. And here's the Cholesky decomposition formula, and basically we have one lower triangular matrix and then an upper triangular matrix on the right. And in the middle is a block triangular matrix. And this one here is the short complement, which has lots of interesting properties on its own. And this, we call it the short complement of L onto C. And this, again, is a symmetric matrix and is supported on the vertex set C. So we can recursively apply the Cholesky decomposition to this short complement. And how do we partition the vertex sets into F and C? All the partitions are determined using the way we've partitioned the vertices on the separator tree. And it just happens that short complements, they have very good properties, especially for this case. So there's transitivity and decomposability, which works really well on this recursive tree. So with that, we can decompose P sub W into something of this form. So every matrix pi here, like pi to the I, that represents something going on the ith level of the separator tree. And basically, we have some matrices that are associated with each node of the tree. Okay, and remember our goal was to be able to write this P sub W as a tree operator and an inverse tree operator. And we want to be able to decompose this matrix based on a separator tree. So this is starting to look really good. And indeed, we can show that the first part is a tree operator. The second part is an inverse tree operator. So what ends up happening is that I didn't define these matrices L superscript H, but they are defined here. They're defined recursively using recursive properties of short complements so that we start off with definitions for the base cases at the bottom, and then this L matrix at the node H10 is going to be just a function of the L matrix at its two children nodes. And now we can talk about solving the matrix maintenance problem. So we want to be able to maintain these L matrices, and there are also some other L matrices, other matrices, and also inverses to be maintained. Because you'll notice here that this is a function of the weights that are changing. But for every bottom level L matrix, notice that it's only a function of the weights on the edges in this piece. So it's quite small, and it gets bigger as we go up. So to maintain these matrices, then we notice that if the weights change at some of the edges, we only need to update the bottom piece that contains that edge and all of its ancestors. So we don't need to update the entire tree. And that's why using this tree structure, we're able to maintain the matrix inverses so much faster than just the brute force maintenance. Okay, and if we very carefully compute the time it costs to do these maintenance, then we get basically the theorem of our upcoming paper in SOTA, saying that for separable graphs, this works out to give us efficient algorithms for solving linear programs. Running a little bit low on time. Okay, so for flow problems, so far we've been talking about the general framework and general linear programs. And for flow problems specifically, we know that if the LP is a flow problem, then this AWA transpose is a weighted Laplacian, because A here will be an adjacency matrix. And with weighted Laplacians, they can be solved in nearly linear time. And also we can take approximate short complements that are sparse. And because of these two tools together, we get nearly linear time min cost flow on planar graphs, and then also m times square root n time min cost flow on tree with T graphs. So we don't get this for general graphs because both of these are lacking. General linear programs. Okay, and now I'm going to skip all of these slides. Sushan told me that I would run out of time, and he was totally right. But it's fun. There's a lot of animation about what happens. Okay, and I didn't talk about implicit representations and heavy hitter detection for this IPM solution X, but both of them rely on this tree structure. So X will be represented as a tree operator applied to a vector. And as the tree operator gets updated, again, we say we don't have to update the entire tree. We don't have to update the operator on every edge. And we can limit the amount of updates and therefore bound the running time. And with heavy hitter detection, so we have X represented as a tree operator times a vector. And the idea here is to sketch the tree operator using Johnson-Lindenstrauss sketch. And it works out magically that we're able to do heavy hitter detection. Okay, and it's been kind of a long line of work, and the theorems are a little bit disjoint, but if you want a nice reference in the future, then hopefully I'll get everything tidied up in my thesis. So shameless plug. Yeah, and thank you.
Thank you. I think we have time for 1 or 2 quick questions.
Just a very simple question. What is the running time then? The nearly linear running time?
Oh, sorry.
Can you be a little bit more specific?
Oh, yeah, nearly linear in the input size. So for planar graphs, because
Is it m times a polylog, or is m to the 1 plus little o of 1?
Oh, m times a polylog.
And what is the polylog? Do you have an upper bound? The degree?
Not that bad, like 3
Okay.
or 4.
Oh, great.
Yeah.
And I guess one more question. I mean, the idea of using separators in Cholesky decomposition goes back to Lipton-Rose-Tarjan
Yeah.
and nested dissection. But clearly you're using much more modern techniques. I'm wondering if you could sort of just briefly say what techniques you're using here. I mean, you mentioned heavy hitters, for example, which was definitely not used, and this tree representation.
Yeah.
Are those the main tools? Are there other tools that you're using on top of the old idea?
I think I covered pretty much all of the main tools. So the heavy hitters for detecting large coordinates when the vector is represented in this tree structure. Yeah, the tree operator and the tree structure. And yeah, I guess that's all. Yeah. But the nested dissection, of course, is very old and it's a seminal piece of work.
Thank you.
More quick question? All right. Thanks, Sally. Thank you for the talk. Now we have a 30-minute break.